Here we will study what are fluxional NMR fluxional molecules. These fluxional molecules are molecules that undergo dynamics, constantly exchanging their positions. For example, PF5, SF4, these are all trigonal bipyramidal geometries. They have trigonal bipyramidal geometries. They undergo very pseudo rotation. That is, it occurs via square pyramidal geometry. The axial, due to this rotation, axial positions become equatorial, equatorial becomes axial, as you see here. The DPP and square pyramidal geometries, the energy differences are very little, therefore they undergo very pseudo rotation to give a functionality, functional character. For example, BF5 fluorine 19 NMR is used to study the pseudo rotation. In this case, carbon 13 NMR is used to study the fluxional character of this molecule. Fluorine 19 NMR is again used to here. The structure of SF4 is obtained from the NMR. For example, at room temperature, single peak is observed. For example, because of constant exchange of axial and equatorial position, they are equivalent. They are equivalent. All the fluorine atoms are equivalent. On lowering the temperature, it splits into two signals. First, it splits into two signals due to axial fluorine and equatorial fluorine are chemically distinct. Further, on lowering temperature, each fluorine, each peak is split into triplet. For example, the axial fluorine are split into triplet because of this coupling with these equatorial two fluorine atoms. Each peak is split into triplet. Let us see quickly a few applications of NMR to inorganic molecules or inorganic compounds. One, metal hydrogen bonding in this complex molecule is established using proton NMR. The nuclear quantum number of rhodium nucleus is 1 by 2. Therefore, proton NMR gives a doublet because of the direct bond coupling gives a doublet. This establishes a bond between rhodium and hydrogen. The structure of phosphorus acid is elucidated by using phosphorus NMR. The formula of phosphorus acid is H3PO3. There are two possible structures I have given here. In this case, phosphorus 15, I'm sorry, this is phosphorus 15, I equal to 1 by 2. And phosphorus NMR, using phosphorus NMR, this compound will give you a doublet, whereas this compound will give you a triplet. The OH protons does not couple because of fast exchange with the water molecules in the solvent. In actually, triplet signal is obtained. Therefore, the correct structure is this one. Similarly, the structure of fluorine fluoroderivative is also obtained. What is the structure of PF6 minus? It is established, elucidated using phosphorus 31 NMR. Sorry, previously I told 15 phosphorus 31 NMR mass number. It gives a septed signal, 7 lines. It reveals that that is fluorine phosphorus NMR. There are 6 fluorine atoms. Therefore, phosphorus couples with the 6 fluorine atoms to give septed signal, 7 lines. It reveals that all the fluorine equivalent. Therefore, the geometry is regular octahedral. pH 4 plus like NH4 plus ammonium ion, phosphonium ion. Using phosphorus 31 NMR, it gives a phosphorus 31 couples with the 4 proton to give quintet 5 lines n plus 1 with intensity ratio. Whereas proton NMR, all the protons are equivalent. It couples with the phosphorus 1 I equal to 1 by 2. Similarly, BRF5, the structure is studied by using fluorine 19 NMR. In this case, there are two peaks were observed with intensity ratio 4:1. It shows that there are two kinds of fluorine. 4 are one type and 1 is a different type. The intense line is doublet. The intense line is doublet because it is tetragonal pyramidal. Then the four equatorial fluorine atoms couple with this proton to give intense signal because of 4 fluorine atoms is doublet. Weak line, this is only one fluorine atom couples with the 4, therefore n plus 1 pinned at 5 lines. Therefore, the structure is symmetrical tetragonal pyramid from NMR studies. NMR is also used to investigate the Cis-Trans isomers. For example, in platinum complex, the cis isomer will have different coupling. Platinum I equal to 1 by 2, phosphorus I equal to 1 by 2, coupling constant. It is cis 3.62. From the coupling constant values, the cis-trans isomers can be determined. In fluorine 19 NMR, the structure of dimethyl phosphorus trifluoride structure is elucidated. At low temperature, two peaks are observed. At room temperature, due to perirotation, fast exchange, only one peak is observed that are all are equivalent. One fluorine in axial position and two in equatorial position. Using NMR, this structure is up. Here we will study what is magic angle spinning. Why it is important in solid state NMR. In solid state, the compound gives broad line in NMR spectrum because of increased line width due to spin lattice relaxation, due to fast spin lattice relaxation, due to dipolar chemical shift anisotropy. These effects are averaged out in solution when the compound is dissolved in solution. These effects are negligible. These effects are negligible. They will give isotropic NMR spectrum because due to rapid tumbling motion. However, in solid state, these effects are very significant. The sample is rotated about this axis, makes an angle with the external applied magnetic field, theta equal to 54.74 degree. The dipolar chemical shift anisotropy is directly proportional to 1 minus 3 cos square theta. When theta equal to 54.74, these two effects become zero. Therefore, the lines are narrowed with the lower line width or obtained. The spectrum is well resolved at this magic angle spinning of the sample. We'll quickly see the EPR spectroscopy. In the absence of magnetic field, the two spin states are degenerate. In the presence of external applied field, the two states splits. The energy of separation is given by, we have seen earlier, G, E, beta, B naught. That beta is the Bohr magneton, G is the E value. B naught is the applied field strength. H nu, the resonance condition is H nu equal to GE beta B naught. The electron spins about its own axis and also rotates, revolves in an orbit. As a result of this, there will be, I forgot to tell, ESR spectroscopy is also called electron spin resonance spectroscopy or electron paramagnetic spectroscopy, resonance spectroscopy, or electromagnetic resonance EMR spectroscopy. How the EPR spectra are presented? Because of this transition between the two electron spin states, there will be an absorption signal. The absorption signal, as you see, it is not well resolved. There are so many peaks, it is buried. So the derivative signal in EPR, the signal is always presented in first derivative. When you take the first derivative of this absorption signal, the hyperfine splitting signals are well resolved. What are absorption and derivative EPR spectra? Why derivative EPR spectra are important? EPR is a very sensitive technique than NMR. However, due to short relaxation time, we have seen earlier, as in paramagnetic system, the absorption signals are always broad, and hyperfine structures we have seen earlier in the slide, hyperfine structures are buried. Therefore, derivative signals are obtained using phase sensitive detection technique to get well resolved hyperfine features. Here I have shown the schematic diagram of EPR spectrometer. It consists of electromagnet similar to NMR, sample holder, and amplifier and detector. In this case, we will use microwave bridge. It is used to generate the microwave, monochromatic microwave. For expand, it is 9.8 gigahertz. For expand, it is 9.8 gigahertz. It will produce Dunn diode. Is used to generate the monochromatic microwave radiation. It uses phase sensitive detector to convert the absorption signal into derivative signal. It is the actual EPR spectrometer. These are electromagnets. This is a microwave bridge, microwave guide, and you have temperature controller, liquid helium to measure low temperature EPR. Similar to spin-spin coupling constant in NMR, in ESR we have hyperfine coupling interaction, hyperfine splitting. It is represented by A, whereas in NMR it is represented by G. It occurs due to the coupling between the spin magnetic moment and the nuclear magnetic moment. We will see further. The spin Hamiltonian for the EPR is H cap equal to H cap E electron Zeeman plus hyperfine coupling interaction. Hamiltonian corresponding to the energy of this Hamiltonian is given by this. We have studied this in G mu B B ms, where ms is the quantum number plus or minus half, and hyperfine coupling term. A is the hyperfine coupling constant. Ms is the magnetic spin magnetic quantum number, nuclear magnetic quantum number Mi. For liquids and gaseous samples, the hyperfine coupling interaction are isotropic because of constant tumbling motion. The anisotropic effects are averaged out as we see in magic angle spinning. For solids, there will be anisotropic. The hyperfine coupling is anisotropic at different angle. Measure will give different value because of anisotropic character. ESR signal further splits into several lines because of this hyperfine splitting as in spin-spin coupling. What are the important characteristics of hyperfine coupling? As the spin-spin coupling, it is similar to spin-spin coupling. It depends on the magnitude of nuclear and electron spin magnetic moments. Electron spin density near the nucleus, because electron spin couples with the nucleus, called a thermic contact term. Similar to J value, A value is independent of applied magnetic field. And n plus 1, it obeys n plus 1 rule. If I equal to 1, then 2ni plus 1. It is similar to spin-spin coupling. The intensity ratio is given by Pascal triangle. In NMR, chemical shift value, similar to chemical shift value in ESR, G value is obtained. For free radicals, organic free radicals, there will be no spin orbit coupling. What is spin orbit coupling? What is spin orbit interaction? As I said earlier, the electron spins about its own axis and also it revolves in orbit. Therefore, the electron is having spin magnetic moment as well as orbital magnetic moment, orbit magnetic moment. These two magnetic moments coupled to give spin orbit coupling, depending on their relative orientation. For free radicals, this spin orbit coupling interaction is negligible. Therefore, the GE value is close to free electron value 2.0023. However, for transition metal complexes, the G values are very much different from the free electron value due to this spin orbit coupling. Let us see an example to illustrate this hyperfine coupling. For example, hydrogen atom. In the hydrogen atom, you have one electron with the spin S equal to 1 by 2 and proton I equal to 1 by 2. In the absence of magnetic field, the electron spin states are degenerate. In the presence of magnetic field, it splits into two, we have seen earlier. And further, the two spin states, each spin state is split into two levels due to coupling between the electron spin moment and nuclear spin magnetic moment. Therefore, it splits into two. In the case of ESR, minus 1 by 2 is the lowest energy state, whereas in the case of NMR, plus 1 by 2 is the ground state. Therefore, by following the selection rule, delta Mi equal to plus or minus 1, there are two transitions. Therefore, there are two signals. There are two signals obtained due to hyperfine splitting due to I equal to 1 by 2. The hyperfine splitting constant is calculated from the spectra as shown here. Let us see few more examples. Cylopentadienyl. Here it is a free radical. It's a paramagnetic molecule. The electron is delocalized. The unpaired electron is delocalized over 5 protons. Therefore, n plus 1 rule. Therefore, sextet, there are 6 lines observed. In the case of benzene radical, the unpaired electron density is delocalized over 6 hydrogen atoms. Therefore, there are n plus 1 septet. There are 7 lines observed with the intensity ratio using Pascal diagram. It is obtained 1, 2, 3, 4, 5, 6, 7. Let us now see naphthalene anion radicals similar to benzene anion radical. Here there are two types of protons: alpha proton, 4 alpha protons and 4 beta protons. Therefore, they have different chemical shift as well as different coupling constant. For example, the coupling constant, hyperfine coupling constant A for alpha proton is 4.9 Gauss, A beta is 1.83 Gauss. The unit for hyperfine coupling constant is Gauss, whereas J in Hertz. The formula used to calculate the number of lines is 2ni plus 1 into 2ni2 plus 1. Therefore, 2 into n4 and proton I equal to 1 by 2. Therefore, there are 25 lines. It agrees with the number of lines obtained in the actual NMR spectra. Here, what is McConnell's relation? This gives the relationship between the hyperfine coupling constant and the unpaired spin electron density. If the unpaired electron spin density is larger, then the hyperfine coupling constant is larger. The unpaired electron couples with the proton. The hyperfine coupling constant is equal to Q rho C, where Q is an empirical constant, proportionality constant. It is for hydrocarbon radical 20 to 30 Gauss. Using this expression, once you know the hyperfine coupling constant from the experiment, Q value is known, you can calculate the unpaired electron density. Rho C will give the unpaired electron density distribution. Using this, we can predict the chemical reactivity site. Here we will study the EPR of DPPH radical. It is an EPR reference compound similar to TMS. Tetramethyl silane is the NMR reference compound. Diphenyl picryl hydroxyl radical is a reference for EPR. It is a field marker. For example, this is the EPR spectra of exchange coupled copper complex. This is the DPPH signal. In the solid state, it occurs as a singlet. It exhibits a single line because of exchange narrowing due to Heisenberg spin exchange. DPPH in the solid state gives a single line due to exchange coupling, exchange narrowing. Okay, let us see the structure of DPPH. The unpaired electron is delocalized over two nitrogen atoms. Therefore, I equal to 1 for nitrogen 14. There are two nitrogen atoms, 2ni plus 1. There are 5 lines with the ratio as obtained here. It is very, very important. And this question was asked in CSIR or GATE. DPH is a field marker. Using this, the G value for since the G value for the DPPH is 2.0023, it is known. Therefore, the G value for the copper complex, iron complex, or any free radicals can be calculated using this as reference compound. EPR of nitroxide radical. These nitroxides are very important organic radical compound used in spin labeling, ESR spin labeling. We'll see further. The unpaired electron is in the nitrogen atom, the oxygen atom, delocalized over this bond. Since nitrogen is NMR active, oxygen 16 is not NMR active. We have seen earlier, In equal to 1, S equal to 1 by 2. Therefore, there are 3 lines. They are of equal intensity. This splits into triplet. E equal to 1, minus 1, 0, 1. The hyperfine coupling constant is given as is calculated as follows. In my research in Medical College of Wisconsin, we have studied on cancer. So we have taken the cancer tissue and put into the EPR tube and measured the low temperature EPR. The EPR spectrum for cancer tissue is shown here. The spectrum is obtained is similar to transferrin EPR, protein EPR. Transferrin is a protein is overexpressed in cancer tissue. As cancer cells require more oxygen for its growth. Using EPR spectroscopy, it is reported that it is used to study the spin crossover phenomenon. It is used to study the spin crossover phenomenon in iron 3 complex. For example, heme. It is present in the active site of several proteins, cytochrome C, myoglobin, hemoglobin, cytochrome C oxidase, etc. This is the high spin ion complex. The G value, this peak, the black one corresponds to high spin. On adding ligand imidazole, for example, it is converted into low spin complex. High spin complex is converted to low spin complex. The G values are this. The peak height decreases. The low spin complex is formed because of it decreases. The spin conversion can be studied using an ESR spectroscopy, EPR spectroscopy. Free radicals are produced in our body in large excess when you suffer from ischemia, heart attack, or any cardiac diseases, neurodegenerative diseases. For example, hydroxyl radical, superoxide radicals, they are extremely short-lived. They cannot be studied by directly by using ESR. So nitrones, TMPO, or simple organic compounds, they react with the hydroxyl radical to form stable free radical, which can be studied by EPR. Here, the free radicals are trapped by the different free radicals are trapped by TMPO, the spin trap. For example, methyl radical, DMPO forms adduct with the methyl radical. It gives a characteristic EPR spectrum. For hydroxyl radical, you will get this characteristic spectrum. From the EPR spectrum, we can determine the free radicals formed. And also, if mixture of free radicals formed, we can do spectral simulation. I have shown how the spectra is simulated in my at the last video, how the ESR spectra is simulated. Using spectral simulation, we are able to suppose a mixture of free radicals formed. Using simulation, we can determine from experimental spectra. How ESR spectroscopy is useful in photodynamic therapy. For example, photodynamic therapy is used for cancer cure. In this photodynamic therapy, photosensitized drug in the presence of light, it is excited and it transfers its energy. It transfers its energy to triplet oxygen to give singlet oxygen, which is highly energetic, which is causing cell death, or or the the excited photosensitizer can transfer an electron to triplet oxygen to form superoxide radical, or it can generate hydroxyl radical. There are two types of mechanism. Type 1 mechanism, formation of free radicals, and the formation of singlet oxygen. Using ESR spectroscopy, the mechanism of photodynamic therapy can be obtained. Similarly, free radical intermediates can be detected only by means of ESR spectroscopy. ESR spin labeling is an important tool to study the dynamics of DNA, RNA, protein molecules. For example, nitroxides on reaction with the SH group, it forms a compound. Now the protein is spin labeled. Therefore, we can follow the using site-directed mutagenesis. We can attach the nitroxide spin and we can study the distance between the two spins used by measuring this spin relaxation time. We have studied T2. We have in Medical College of Wisconsin we have developed, they have developed ESR instrument, saturation recovery instrument, to calculate the spin relaxation time and spin lattice relaxation time. Using that, they will study the spin labeling and the protein structure. Using the ESR spectra of the nitroxide radicals, spin labeled nitroxide radicals, it is freely tumbling from the line width, from the line shape. We are able to study the dynamics of proteins or small molecules. The EPR spectra of different copper complexes. For example, A is the EPR spectra of tetragonally elongated complex, and B is the tetragonally compressed copper complex, and this is orthorhombic complex, low symmetry copper complex, and this is exchange coupled copper complex. Let us now see these. For example, in the case of copper, I equal to 3 by 2. So there will be 4 lines. I equal to 3 by 2, 2 into 3 by 4 lines, as you see here. 1, 2, 3, 4. This is G parallel. For example, this is G parallel. This direction is G parallel. And this direction and these two directions are G perpendicular. Therefore, there are two G perpendiculars. The signal is more intense, whereas the hyperfine coupling, because the electron, the unpaired electron present in copper couples with the copper nucleus to give 4 lines. This is the hyperfine coupling constant. In this case, in G perpendicular, it is not resolved. Here in copper complex is JT active, is it is undergoing strong John-Taylor distortion. Therefore, and the axial ligands are elongated, axial bonds are elongated, the equatorial bonds are compressed, and G parallel value is greater than, if G parallel value is greater than G perpendicular, then it is tetragonally elongated copper complex. Under certain conditions in the crystal constraint, lattice constraint, there are also copper complexes in JT compressed state. In this case, G perpendicular is greater than G parallel. If G perpendicular is greater than G parallel, then it is tetragonally compressed complex. In the case of uh, orthorhombic, less symmetric complex, G1, G1, G2, G3, they are not equal. G1 not equal to G2, G2 not equal to G3. And in the case of pure copper complex, there will be exchange interaction between the neighboring copper ion to give exchange coupled narrowed single line. We don't get 4 lines. It is expected to give 4 lines, but due to exchange coupling, we only get single line as shown here. EPR spectra of vanadium ion, it is a D1 species. The I value for vanadium is 7 by 2. Therefore, the unpaired electron couples with the vanadium nucleus to give 8 lines. The solution EPR of vanadium EPR at room temperature, it gives 8 lines as shown here. At low temperature, the same solution at low temperature, it gives it is also tetragonal complex. Therefore, you will be getting G parallel, G perpendicular. You see G parallel, G perpendicular, similar to copper complex, and A parallel, A perpendicular. For powder, low temperature EPR of in the powder, all the orientations are possible. So you will get magnetic field perpendicular to the tetragonal elongation axis or x-axis, y-axis perpendicular. So you will get G parallel, G perpendicular. In case of solution EPR, it is isotropic because of tumbling motion. The spectrum obtained is isotropic, whereas the spectrum obtained in the case of powder EPR at low temperature or solution at low temperature, it gives anisotropic because of the orientation of the molecules at low temperature. In Medical College of Wisconsin, I have studied the thiol oxidase activity, peroxidase activity using pulse EPR, NMR, ENDOR, etc. We have studied the changes in the structure of the active site during the peroxidase activity, thiol oxidase activity, published this paper in Biochemistry Journal. Using NMR and ESR, we are able to study the free radicals formed during these activities. Superoxide dismutase, we have used the copper zinc because in ALS disease, in paralytic attack, amyotrophic lateral sclerosis, it is nothing but a paralytic attack where free radicals are generated. This enzyme, copper SOD1, copper zinc superoxide dismutase enzyme, is involved in this neurodegenerative disease. So we have studied the mechanism of peroxidase activity, thiol oxidase activities for the first time using EPR, NMR studies. During peroxidase activity, in addition to superoxide dismutase activity, this enzyme also possesses peroxidase activity in the presence of hydrogen peroxide and bicarbonate. It is present in our blood, in our cells. For example, this is the one-dimensional proton NMR. We have assigned the active site. This is the active site of the SOD1 protein. We have assigned histidine 44, 46. And this is the NOC, 2D NOC spectrum. What are the changes in the active site during the peroxide activity? We have identified, we have investigated and published. Similar to peroxidase activity, thiol oxidase activity of SOD1 was studied by our group using spin trapping method as well as ESR, ENDOR, electron nuclear double resonance spectroscopy, and NOC NMR spectra. We have also used advanced EPR techniques to study the active site changes, active site geometry changes in SOD1 during thiol oxidase activity and peroxidase activity using 3-pulse eSIM electron spin echo modulation spectra, 4-pulse high score spectra shown here. We have used electron nuclear double resonance spectroscopy ENDOR and EPR to directly probe the copper active site and free radical formed during the bicarbonate dependent peroxidase activity and published in Journal of Biological Chemistry. Using low temperature EPR, we have identified the tyrosyl radical formation when bovine SOD1 superoxide dismutase, copper zinc superoxide dismutase, is exposed to UV light. Tyrosyl radical is produced. Using simulation, the parameters are obtained. And in the case of wild type human SOD, a tryptophan radical is obtained. Using simulation, we have identified this as a tryptophan radical. We have also produced mutant. Tryptophan is replaced by phenylalanine, phenylalanine. In that case, no tryptophan radical is obtained. It is obvious. We have replaced the tryptophan by phenylalanine. Therefore, there is no tryptophan radical is formed on exposure to UV light. So, ESR spectroscopy is very much used in studying the free radicals protein dynamics, and has got lot of applications. I have received more than 1 crore funds from various funding agencies. SERB DST recently I have received, and the Department of Biotechnology New Delhi I have received grants 2 times from Department of Biotechnology, and the DRDO New Delhi, DRDO DIPAS New Delhi, and UGC. Without my PhD boss guidance, I would not have achieved this. I am very, very thankful, grateful to my PhD boss, Professor R. Muriesan. I am also very, very thankful to my US boss, Balaraman Kalyanaraman, Professor Balaraman Kalyanaraman, Chairman, Biophysics Department, Director, Free Radical Research Center, for giving me this wonderful opportunity, for teaching me and training me to achieve this. I have carried out all my research works with our collaborative researchers. I thank all the collaborative researchers for making the research achievements. Finally, I thank all my research scholars, former research scholars and present research scholars for their support and for their hard works. They are now in USA. Thank you all the participants for patiently listening and watching the sessions. Finally, I again thank the organizers for giving me this opportunity to share my research and teaching experience with you, all the participants. Thank you all.